This is Sentinel. 60 Nmap commands, 27 minutes, 1 live lab. No boring theory, no endless slides. Just real commands, real targets, and real results. We're testing network discovery, stealth techniques, firewall behavior, and attack surfaces across isolated Windows, Ubuntu, and Metasploitable machines. Everything is running inside a private VirtualBox lab for educational purposes. 60 commands, 27 minutes. Let's start. Command 1. The foundation. The most basic scan. We just type nmap followed by our target IP, 192.168.56.106. Why start here? Because by default, Nmap automatically scans the top 1,000 most common TCP ports. Look at the screen. In just 2.27 seconds, we have our result. The system tells us 998 ports are closed, but port 22 for SSH and port 3000 for PPP are wide open. In a real-world external pentest, these two open ports would be our immediate attack vectors. This is basic reconnaissance. Command 2. Who else is hiding on our network? In a real scenario, you rarely know your target's exact IP up front. We need to map the environment. We use the -SN flag, also known as a ping scan. We are telling Nmap, don't waste time checking ports. Just sweep the entire subnet and tell me who is alive. Look at the output. In 7.42 seconds, it swept all 256 addresses. And we have exactly 6 active hosts on our network. This confirms our primary targets at the 105, 106, and 107 addresses are up and running. Command 3. Surgical precision. Sometimes we don't need all the noise. If you're specifically hunting for web servers, scanning thousands of ports will just trigger the admin's alarms. To stay quiet and save time, we use the -P flag followed by port 80. Our request to the Metasploitable machine came back in just 2.12 seconds, confirming that port 80 is indeed open for HTTP traffic. Fast, clean, and highly targeted. Command 4. Scanning a specific range. What if we only want to check the most critical system ports? They usually reside within the first 1,000. By typing -P1-1000, we scan our Windows 10 machine strictly within this boundary. The result shows that out of 1,000 ports, 995 are closed, but critical Windows services like port 80, 135 for MSRPC, 139 for NetBIOS, 443, and 445 are sitting wide open. We know exactly where to strike. Command 5. The exhaustive sweep. Nothing stays hidden. Imagine a clever sysadmin hiding critical services on high, non-standard ports to avoid detection. How do we find them? We use -P-. That single dash tells Nmap to relentlessly scan every single one of the 65,535 available TCP ports. It's loud, but it works. Look at the result. In 14.21 seconds, we've exposed every secret on the Metasploitable system. We're not just seeing the standard port 22 or 80, we've uncovered unknown services hiding way up on ports 8180, 8787, and even 53541. Command 6. The mistake. In cybersecurity, one missing letter can ruin an operation. Watch the screen closely. I tried to scan a TCP port 80 and a UDP port 53 at the same time. But look, a yellow wien ring popped up in the terminal. What is Nmap telling us? You requested a UDP port, but you forgot to include the -SU flag for UDP scanning. Look how smart this tool is. It caught the error, ignored the UDP request, and just returned the TCP result. Always double-check your syntax. Command 7. The race against time. In live operations, time is your most expensive resource. If you don't have time for a full 1,000 port scan, you use -F for fast mode. Nmap uses its internal database to filter down and scan only the top 100 most commonly exploited ports in the world. And the result? Our Windows 10 machine was scanned in a blazing 3.23 seconds, handing us the most critical attack surfaces on a silver platter. Command 8. Live monitoring. When your scan is targeting hundreds of machines and taking hours, you can't just stare at a blank terminal. You need to see what the system is doing in the background. We achieve this with -V for versus mode. Now, instead of waiting until the very end, Nmap instantly prints discovered open port to the screen the exact millisecond it finds one. This gives you absolute real-time control over the operation. Command 9. The microscopic view. If one -V gives you updates, what does double verbose -VV do? It explains exactly why Nmap is making its decisions. Pay attention to the output. It doesn't just say port 22 is open. It explains why it thinks it's open, explicitly stating SYN-ACK TTL64. This means the target server actively replied to our probe with a positive SYN-ACK flag. You aren't just using a tool, you are watching network protocols talk to each other. Command 10. The missing list. Mass scanning. Hackers don't sit there typing dozens of IP addresses manually. They load them all into a text file and feed it to the scanner. Let's type -il-targets.txt and the terminal throws an error. Failed to open input file targets.txt. File not found. The reason is simple. I forgot to actually create the target list file before running the command. The software won't think for you. Always prep your workspace and verify your files before launching an attack. Command 11. Full connection. Loud but reliable. The most classic port scanning method is -ST, the TCP connect scan. Nmap completes the full three-way handshake with every single port. It's incredibly reliable, but I guarantee you will leave massive footprints in the target's firewall logs. Let's check the screen. In 2.29 seconds, we successfully mapped every open port on the Metasploitable system, from 21 FTP all the way up to 8180. Command 12, Ninja Mode. What if you don't want to end up in the security logs? We use -SS, the S-WINE stealth scan. In this mode, Nmap never finishes the connection. It sends a S1 packet, gets the response, and immediately drops the connection before it's logged. On our Ubuntu machine, this command executed in a stealthy 2.22 seconds, silently finding port 22 and port 3000 without raising alarms. Command 13. The UDP headache. Watch carefully. We are scanning UDP ports with -SU. Notice how the process completely froze. Look at the terminal. 6 minutes and 36 seconds have passed, and Nmap says it's only 45.53% done. Why? Because UDP is connectionless. Firewalls silently swallow the packets, and Nmap just sits there waiting, thinking maybe the packet got lost, retrying endlessly. We are hitting Ctrl+C. We don't have time for this. Command 14. The UDP speed hack. Let's take control. To make UDP scanning viable, we add -F to scan only the top 100 ports and -T4 to force aggressive timing. Even though Nmap warns us about retransmission cap hit, we pulled the results in just 31.08 seconds. We successfully confirmed that the 137 NetBIOS-NS port is wide open via UDP on our Windows 10 machine. Command 15. Unmasking the services. Knowing a port is open is useless if you don't know what's running behind it. We need the exact software version to find an exploit. The -SV flag performs service version detection. In 13.93 seconds, it revealed that port 21 isn't just FTP. It's explicitly running VirusFTPD 2.3.4, and port 80 is running Apache HTTPD 2.2.8. This is exactly the intelligence a hacker needs to find a working payload. Command 16. The deep interrogation. In our previous scans, Ubuntu's port 3000 just showed up as a generic PPP service. Let's apply pressure. By adding Missions Intensity 5, we force Nmap to interrogate the port heavily. Look at the screen. In 13.58 seconds, Nmap didn't just identify the service. It ripped the raw HTML code right out of the web page, fully exposing that the famous vulnerable OWASP Juice Shop application is running there. That is brilliant analysis. Command 17. The light touch. If high intensity alerts the target or takes too long, you use version light. We scanned our Windows 10 machine using this fast, lightweight method. In 16.76 seconds, we easily identified Apache HTTPD 2.4.58 on port 80 and the MariaDB database running on port 3306. Command 18. Maximum effort. Let's unleash Nmap completely. The version all flag throws every single detection probe in Nmap's database at the target. In 13.6 seconds, we stripped the Metasploitable system bare, generating a highly detailed report that exposes exact database versions like MySQL 5.0, 51A, and PostgreSQL 8.3.0. Command 19. Two birds, one stone. Why run two scans when you can run one? We combine version detection -SV and operating system detection -O. In just 14.97 seconds, we needed to know what architecture our Ubuntu system was running. Nmap proudly prints operation system details, Linux 4.15, 5.19, right to the terminal. We now hold the target's complete technical passport. Command 20, Aggressive Mode. This is why Nmap is the king of scanners. We trigger the -A flag. With one command, it simultaneously performs OS detection, version scanning, script scanning, and traceroute. Look at this massive 28-second analysis. It instantly warns us that anonymous FTP login allowed is wide open, identifies the exact Samba SMMBD 3.0.20 version, and even dumps the expiration dates of the SSL certificates. This isn't just a port scan, it's a full-scale intelligence operation. Command 21. Targeting Windows SMB. If we are hunting Windows networks, we focus on the weakest links. Ports 139 and 445 are the standard for file sharing and printers via the SMB protocol. In just 8.71 seconds, we confirmed that both the NetBIOS SSN and Microsoft DS services are active on our Windows 10 target. Why is this critical? Because devastating ransomware like WannaCry and the Eternal Blue exploit use these exact ports to compromise millions of systems worldwide. Command 22. OS fingerprinting. Let's find out exactly what build of Windows we are dealing with. The -O command analyzes the specific way the target responds to TCP/UDP packets, its fingerprint, to determine the OS. In 4.71 seconds, Nmap confidently mapped this machine as Microsoft Windows 10, specifically pinning it between builds 1709 and 21H2. This level of detail even hints at whether the system is fully patched. Command 23. The art of guessing. Systems don't always give themselves up easily. Hardened servers often drop packets to avoid detection. What do we tell Nmap to do? We use ~o-scan-guess to allow it to make an educated assumption. In 3.58 seconds, Nmap analyzed the Metasploitable machine and cross-referenced its database to guess that it is running a Linux kernel between 2.6.9 and 2.6.33. Even when the scanner isn't 100% sure, it gives you the best possible intelligence. Command 24. The time saver. When auditing a corporate network with thousands of endpoints, you cannot afford to waste time analyzing dead hosts. The ~os-scan-limit flag is irreplaceable. It tells Nmap to only attempt OS detection on hosts that have at least one open and one closed port. The perfect conditions for an accurate read. Our Ubuntu machine met the criteria, and in 3.62 seconds, its Linux 4.15/5.19 identity was confirmed. Command 25. Mapping the route. How far away is our target? Seeing the routers and hops between our machine and the target is vital for security analysis. We use the ~traceroute command to map the path. Look at the screen under the traceroute section. Our target is just one hop away, sitting at a 3.19 millisecond distance. If we were scanning across the internet, you would see dozens of intermediate IP addresses listed here. Command 26. The invisible trace. What if you want to find the exact route to a device without poking its ports and triggering security alarms? We combine -SN, do not port scan, with ~traceroute. Instantly, in just 2.08 seconds, we mapped the location of the Ubuntu machine with a blazing 0.74 ms ping speed, a flawless geographical trace with absolutely zero port noise. Command 27. Local network dominance. On a local area network, standard IP packets aren't always the best choice. ARP scanning is the ultimate, guaranteed method for local discovery. The IFTPR command sweeps the network using ARP requests, which no local operating system firewall can block or hide from. Although sweeping the entire subnet took 13 seconds, the result is definitive. Out of 256 possible addresses, it mapped exactly 6 active devices in real time. Command 28. Bypassing ICMP blocks. What do you do when a strict firewall blocks all traditional ICMP pings? Most computers will appear dead to the scanner. This is where UDP ping shines. Using -PU53, we send a probe directly to port 53, the DNS port. Firewalls almost always allow DNS traffic through. And look at that, the Windows 10 machine revealed itself, returning a response in just 0.022s latency, confirming the host is up. Command 29. The classic ping. Sometimes the simplest tool is the most reliable. We use the -PE flag to send a standard ICMP echo request to the target. This is the most widely used method to verify if a system is online. As you can see on the terminal, the Metasploitable system replied in 2.29 seconds, proving our request traveled and returned with a latency of just 0.0020s. Command 30. Nmap's X-ray machine. Watch the screen closely. If you want to see exactly what Nmap is doing behind the scenes, ~packet-trace is your X-ray vision. Look at this massive flood of data hitting the terminal. From the initial ARP requests to hundreds of TCP connections, you see every CENT and RCVD line. We are watching every single byte of data leaving our machine and returning from the target live. When a scan fails or a firewall blocks you, elite engineers read this raw traffic trace to find the exact point of failure. Command 31. Exposing the reasoning. How does Nmap actually know a port is open? It doesn't just guess. By adding the double reason flag, we force the scanner to justify its results. Look at the terminal. Next to every open port, it explicitly prints SYNACKTTL64. This proves that the target machine actively responded to our TCP/SYN packets with an acknowledgement. Trust, but verify. Command 32. Unleashing the Nmap Scripting Engine. Port scanning is just the beginning. The -SC flag runs a batch of default, safe scripts against the target. It's like sending an army of automated mini-hackers. In 79.83 seconds, it extracted SSH host keys, identified the MySQL salt, and flagged that anonymous FTP login is permitted. We are moving from reconnaissance to active vulnerability hunting. Command 33. Auditing authentication. We want to know how the target system allows users to log in. We run the authentication scripts against our Ubuntu machine. Instantly, Nmap probes the SSH service on port 22 and reveals the supported authentication methods, public key and password. It even checks if any public keys are accepted by default. This tells us exactly which brute force methods might work. Command 34. The system crash. Watch closely. I trigger the default and safe scripts simultaneously, and the terminal completely crashes. ZSH, segmentation fault. This is raw cybersecurity. Sometimes, the scripts within Nmap have memory management conflicts with the operating system when querying specific targets. When your tools break, you don't panic. You drop the unstable script and move to the next vector. Command 35. Hitting Windows where it hurts. When you are auditing a corporate environment, the SMB protocol is usually your goldmine. Instead of just guessing the OS, we run the SMB OS discovery script. In exactly 2.69 seconds, Nmap reaches directly into the Windows 10 machine and pulls out the exact operating system details over the network. If a system administrator left SMB exposed, they just gave us the blueprint to their machine. Command 36. Now that we know it's Windows, we throw every known SMB vulnerability script at it using the wildcard SMB-VULN*. This checks for devastating flaws like MS-10061. But look at the result, taking 7.75 seconds. Could not negotiate a connection, failed to receive bytes. What does this mean? The Windows 10 firewall, or patching system, actively rejected the malicious payload negotiation. The defense held up. We have to find another way in. Command 37. Reading the web without opening a browser. If you visit a target's IP in Google Chrome, you leave browser fingerprints in their access logs. We don't want that. We target port 80 using the HTTP-title script. In just 2.20 seconds, Nmap quietly grabs the hidden web page title, returning Metasploitable 2 Linux. We now know exactly what web application framework is running without ever visiting the site. Command 38. Web administrators often think hiding a folder makes it secure. Let's prove them wrong. We use the HTTP-enum script to blindly brute force hidden directories on the web server. In just 4.97 seconds, Nmap exposes critical, unlinked folders. Look at the terminal. /phpMyAdmin //doc/ and /tikiwiki/ are sitting right there. We just mapped the web server's internal admin structure without a single click. Command 39. Testing the front doors. File transfer protocol on port 21 is notorious for misconfigurations. The FTP anon script checks the most common one. Look at the output. Anonymous FTP login allowed. The server is literally letting anyone log in without a password. In a real-world scenario, this is where you drop a reverse shell or extract sensitive company data. Command 40, the brute force assault. If there are no easy misconfigurations, we force our way in. We launch a relentless SSH brute attack against the Ubuntu system. Look at the terminal. This is automated intrusion in real time. Nmap is firing hundreds of login combinations per minute. Root, admin, user, password. It is actively battering the SSH port, testing the strength of the target's password policy. Command 41. Moving to the back end. Databases are the crown jewels of any network. We aim at port 3306 and run MySQL-info. In a lightning-fast 2.14 seconds, we don't just see that MySQL is open. We pull the exact 5.0.51/3 Ubuntu 5 version, its capabilities, and most dangerously, we expose its cryptographic salt. We are gathering the puzzle pieces needed to break their encryption. Command 42. The Holy Grail. We drop the hammer. We run the legendary double script vuln. Notice how this scan takes much longer, nearly 5.5 minutes. It is aggressively testing the system against a massive database of known exploits. And look at the screen bleed red. The scan rips the target apart, revealing the infamous VirS FTPD version 2.3.4 backdoor, the SSL Poodle information leak, and CCS injection. It even found a Trojaned Unreal IRCD backdoor. This machine is completely compromised. Command 43. Nmap is not just a scanner, it is a weapon. Finding a hole is one thing, proving it can be breached is another. By running the exploit script, we command Nmap to actively test the attack vectors it just found. In 42 seconds, it verifies the VirS FTPD backdoor and attempts to establish a foothold. We have crossed the line from passive reconnaissance to active exploitation. Command 44. The raw reality of hacking. Watch closely. I try to run the not intrusive scripts against our Ubuntu target, and boom, the terminal completely crashes, throwing a ZSH segmentation fault. This is unfiltered cybersecurity. Sometimes, complex script loads cause memory management failures between Nmap and your operating system. When your tools break in the field, you don't panic. You adapt, drop the unstable script, and keep moving. Command 45. The human error. I command Nmap to execute a highly targeted brute force attack using my own custom dictionaries. The result, error parsing username list, users.txt, no such file or directory. I failed to prepare my payload files before launching the attack. The scanner is an unforgiving machine. It demands absolute precision. Always prep your workspace. Command 46. The privilege block. I try to update the Nmap vulnerability database to get the latest scripts by typing /script-update db. The system fires back. Permission denied. Why? Because modifying the core security database requires root privileges. You cannot bypass local security policies without using sudo. It's a reminder that even the attacker must follow the rules of their own operating system. Command 47. Advanced evasion tactics. How do we bypass a strict intrusion detection system? We shatter our footprint. The -F flag fragments our IP packets into tiny, 8-byte pieces. When these broken fragments hit the firewall, it becomes incredibly hard for defensive filters to assemble and read the malicious signature. In 2.82 seconds, we slip right through the net. Command 48. Total control over the network layer. To be even stealthier than standard fragmentation, we use $MTU24. This manually forces the maximum transmission unit to just 24 bytes. The result is a highly customized and unusual packet stream, and Windows 10's deep packet inspection is completely blinded by the weird traffic. We retrieve the open ports in just 2.64 seconds. Command 49. Smoke and mirrors. If you don't want the admin to block your IP, you mask it. We use the -DRND:10 flag. This incredible feature hides our real scan behind 10 randomly generated fake IP addresses. When the Ubuntu server's security logs check who's scanning them, they see a chaotic flood of 11 different IP addresses, making it nearly impossible to pinpoint the real attacker. Command 50. Framing the innocent. Random IPs are good, but specific decoys are better. We tell Nmap to make the scan look like it's coming from the Windows machine, the Ubuntu machine, and our real IP labeled as ME, all at the same time. The Metasploitable system thinks its own trusted network neighbors are attacking it. This is how you weaponize internal trust. Command 51. The total spoofing attempt. We try to completely fake our source IP using the -S flag, making it look like the Windows machine is doing the scan alone. But Nmap throws a critical warning: failed to determine route. This is a vital networking lesson. You cannot perfectly spoof an IP address if your machine's routing table isn't explicitly configured to handle the return traffic for the deception. The packet can be faked, but the network still needs a route back. Command 52. Disguising the attack vector. Firewalls are paranoid, but they often blindly trust certain types of traffic, like DNS. By using --sourceport 53, we manipulate our packets so the firewall thinks our invasive scan is just harmless domain name system traffic. The security rules let us right in, and we map the target in just 2.64 seconds. Command 53. Breaking the signatures. Advanced firewalls know what a standard Nmap packet looks like, based on its exact size. So, we change the size. After a quick typo correction in the terminal, we use --data length 25. This injects 25 bytes of random garbage data into every packet. The firewall's signature database no longer recognizes our traffic, and we bypass the alarm systems. Command 54. Scrambling the radar. When you scan an entire subnet, going sequentially from IP.1 to 255 can trigger automated defense systems almost instantly. Because the traffic looks artificial, we use --randomize hosts to scramble the scanning order across 256 IP addresses. Instead of moving in a predictable sequence, the scan sweeps across the network in a completely unpredictable, chaotic pattern. making it much harder for sequential detection algorithms to identify the scanning pattern. Command 55. Probing the armor. At the local network layer, your MAC address is your true identity. We try to spoof it to an unknown vendor using --spoof-MAC0. But look at the result. Host seems down. The Windows firewall or the network switch caught the unusual MAC address and dropped our connection. This is an important security lesson. True security systems don't just watch IP addresses. They watch the hardware too. Command 56. Testing packet integrity. We send intentionally corrupted packets using --badsum. If a system replies to a packet with a bad checksum, it can reveal that the traffic isn't being properly filtered, but our target ignores all 1,000 ports, returning filtered. That tells us something important. A security device is sitting in front of the target, inspecting the traffic before it reaches the host. Every packet is being checked, and anything that fails the integrity check is dropped. Command 57. Mapping the rules. The -SA TCPACK scan isn't meant to find open ports. It's designed to map out firewall rule sets. By sending an acknowledgement packet out of nowhere, we wait to see what the firewall does. Does it drop the packet, or does it send a reset? In our test, all 1,000 ports are reported as unfiltered on the Windows machine. That gives us critical intelligence. The firewall is not actively blocking our specific IP range. The rules are mapped. Now we know where the barrier isn't. Command 58. The ultimate stealth sequence begins. We send a null scan using -SN with absolutely zero TCP flags set. It's an unusual packet, one that shouldn't normally exist. Windows drops it, but the Linux-based Ubuntu machine reacts differently. It returns an open or filtered response for our target ports. We are exploiting a fundamental difference in how operating systems handle unexpected protocol traffic. Same packet, different operating system, different response. Command 59. The infamous Xmas scan. If zero flags didn't work, what about all of them? We use -SX. This sets the FIN, PSH, and URG flags simultaneously, lighting up the packet like a Christmas tree. This chaotic packet is designed to bypass standard, poorly configured router firewalls, especially those that only look for SYN packets. Different flags, different packet. Different detection challenge. Command 60. For our final command, we execute the Ghost protocol, -T0, the paranoid timing template. Look at the terminal. I hit space, but it's completely frozen at 0.00% done. Nmap is now waiting 5 full minutes between sending every single packet. The goal? To minimize detection by Intrusion Detection Systems. A full scan like this could take weeks to finish. So, we're pulling the plug here. And that's Command 60. Exactly 27 minutes. 60 practical, raw, and sometimes broken commands, executed in a live lab. You saw firsthand that real cybersecurity isn't a movie. Files go missing. Syntax errors happen. Scripts crash, and firewalls fight back. The true skill lies in how you troubleshoot and how you adapt when those defenses fight back. So, which of these 60 commands was your favorite? And which one are you going to test in your own lab? Let me know in the comments below. If this operation upgraded your arsenal, hit the like button and subscribe to Sentinel. Keep your defenses strong, and I'll see you in the next operation.